perhaps not enough resources there, because this takes a lot of computational time.
Alternatively, if you're trying to run the code during this session, in this case, when pretty much everyone is doing the same thing at the same time, what you could do is make the small version of the data set even smaller. That was one line near the beginning. I think it was around line 100. There we specified the fraction of the whole data set that should be kept in the smaller version. Currently, it was set to 10%. We're making it even smaller, than even the more involved methods should at least finish computing, even though the results will obviously not be quite as good. But this is just for learning. Yes. We're not trying to get the last bit of performance here.
Yes, that's a very good point. So just for the purposes of trying, you can leave it running, but with a smaller version of the data set, and your results are perhaps not gonna be the same as we had in the slides, or as those that we showed, but at least it's going to run. So in our own local machines, that also took quite some time.
Yes.
Yeah, so that's what I was saying. He made it with a small sample. So what you can actually do is make the small sample even smaller. So let me share my screen here with you, and then we can go through the point in the code where which Sebastian also mentioned. I think that was, you said, Sebastian, right around line 100, right? Yeah. So
95.
So let's go here. You should see now my RStudio. So that's basically the place here, right? So we say we're making a small version of the training data set, and we say we take 10% of the total number of observations that we have in the loans train. And I might want to say, okay, I make this even smaller. So instead of 10%, maybe I will just take 5%, or maybe even less than that, 3%, and that's going to make the data set a little bit smaller. So that's probably something that you can try.
There was also another question. If my online tool is translating correctly, this is referring to the validation matrix. There are actually two different things that you could mean by this. One of the tools that we introduced at the very beginning was this splitting the data into a training set, a validation set, and a testing set. And that was intended for making sure that the model does not cheat by testing it and checking it on data it has already seen. Another different tool is the confusion matrix, which we use during classification problems to find out, okay, so when was the model correct, both for positive outcomes and for negative outcomes? There's no such thing as a validation matrix as far as I know, so I'm not exactly sure which one of those two you would like to hear more about. But maybe you can elaborate. Cross-validation, right.
All right. So maybe let me stop then the sharing here, so we can actually get to either the slide, or perhaps we can even share a whiteboard. So let's do a little bit of drawing. You should see a blank screen now.
Yes.
If things work correctly. Okay, great. So I apologize in advance for my very bad skills in drawing that almost got me kicked out of engineering school back then, but I hope you still can understand what I'm going to draw here. So basically, so your question was about cross-validation, right? So the idea is, well, imagine we have a sample here. So for easy of exposition, let's say we have 10 observations in the sample, right? So and we can apply the same logic further if we have not 10 but 100, 1,000, or several thousand. So the same logic would apply. So basically we're gonna split this sample here. So let's go, I have 3, 4, 5, oops, sorry, 6, 7, 8, let me count that,
Exactly.
3, 6, 7, 8, yeah, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, missing another one, 10, right. So now we have 10 different parts. I'm trying to make this a little bit more beautiful. Not gonna work, okay. So that's what we have here in our sample, right? And the idea then now is to say, how do I split this sample so that I can make the best of it? So instead of feeding all these 10 observations to my model and using all of that as a training data, let me get it in such a way so that first I'm going to use all 9 observations. So I'm going to just randomly pick 9 out of those, for example, and I'm going to leave one of them aside that I'm going to use to test the data set out, to test my results afterwards. And then in the next iteration, this one here is going to be part of my training sample, and I'm going to leave another one to be part of the testing of the validation sample. For example, this one here. And we're going to repeat this all over again until all of them were once part of the validation sample. So in the end, by doing that, what I end up doing is I end up training 10 models. And that's why this takes so long, because in every model, I'm going to leave one of these chunks of data aside and use the 9 other chunks. So using 9 observations to train the model, 1 observation to see how well do I do of a job on new information, so new data that the model did not see yet. And then the next time, it's going to be another observation that I'm going to leave aside. And the next time, yet another observation. Until in the end, I went through all of those observations so that each one of them was once part of this new data that we left aside to validate the model. Okay, so that's the idea here. And that's why this takes a little bit longer than not doing cross-validation, because if you're not doing cross-validation, what we would do is just to say, I'm taking all these 10 observations and train the model.
Well, ideally, you would still keep one chunk of the data aside for validation. Basically, the very first thing we introduced was this training, validation, and test split. This cross-validation is an alternative to the training validation split. It's doing it a little bit more involved, more models, but the advantage we get out of this is we are offsetting some of the individual outliers in the data set. We're getting a whole bunch of different models. So we are actually getting some sort of confidence interval on the performance of our model. The only trade-off is it takes 10 times as long.
Sure, that's a very good point, right? So this is part of the data set that you originally set aside for training. So this shouldn't be the entirety of the data that you have available, because if you put everything in here, then in the end you have nothing, for example, to test the model. So what would typically do, as Sebastian said, you either just say, I have a train and test, all right? Or you can say, okay, I'm actually going to keep following this idea of train, validation, and test. But in the training process, I'm doing that here. So this is also possible, right? So that you typically only have something to gain by doing cross-validation. But again, that takes a little bit more time, so that will require more computational power. I hope that that made things a little bit clearer, Nestor, or do you have a follow-up question on that? So please do let us know if that helps. Then we have other questions here. So I think Raul came first on the Q&A. So he's asking, so I've used an ensemble method, majority voting rule, on 3 different trained models in a sentiment-based risk indicator for the Mexican financial sector, Latin American Journal of Central Banking. It helps us to improve slightly most measures. What I don't get exactly is, what is the boosting method ensemble? Could you please elaborate on that? Could you give me an example, I think simple example with a tree, with let's say 3 deep levels? Yes, sure. So just one question there. What kind of ensemble did you use there? So I'm guessing, as I saying, you're using a majority voting. You probably did something in the spirit of bagging, right? So I imagine either that, or you used 3 different models on the same data, and afterwards use majority voting for the results, I would imagine, right?
It sounds to me also like that. Perhaps they're even using different model structures, maybe an entirely different thing, but it sounded like they were training all of them on the same data without, yes, on the same sample without any interaction between these 3 different models.
All right.
So,
yeah, please, Sebastian, sorry.
No, you got the script. Go ahead.
Yeah, okay. So in that case, so how does that differ from boosting? So perhaps let's try to draw what you did here, right? So imagine your base models were trees. So let's make this, or perhaps let's say it's 3 different models, because if they were trees, if they're seeing the same data, then, and if they have the same hyperparameters, then you would literally get 3 times the same tree, right? So let's say, for example, you have one model was, let's say, a regression. Let's say this is plus B2 times X2, etc., etc. And then you had, let's say, a tree. And you had, let's say, what else could you have had? Perhaps you also had, let's say this was perhaps a linear regression. This was a tree. Let's think of something else. Maybe you also had a another model, let's say, with a, sorry?
Support vector machine, something will.
For example, yeah. So you had a support vector machine. Good, that's it. So let's say that this is, so you had something. I'm trying to draw here like the typical picture that we associate with a support vector machine, right? So okay, so good. So you had that, and then you have the votes. So let's say this is the vote of the model number 1. This is of the model number 2. This is of the model number 3, right? And in the end, you just got the majority voting here, right? Now, how does that differ from boosting? Because this idea is also the same thing that we apply when, or very similar, that we apply when we talk about bagging trees, right, or bagging models. And the only difference is that you wouldn't use the same data. So instead of saying, well, let's say this is my data set. So in what you mentioned here, you got the same data set showing up for these 3 different models, right? Now, if I'm using the same method, which is, for example, the case in random forest or bagged or bagged trees, random forest, something that we're going to discuss today, then I would literally get the same tree all over again. So what we do in bagging is that, we slightly change some of the samples here so that the trees can be slightly different. But as we have seen yesterday, in fact, that typically still tends to lead to models that are very, very similar to one another. Now, how does boosting differ from that? What I'm doing in boosting is I'm not running 3 competing models that are going to have their votes independent of one another, because that's what's happening here, right? I can estimate these 3 models independently from one another and then see what do the most votes say, right? Now, with boosting, what I'm doing is I'm doing this sequentially. So let's imagine, for example, in the context of a tree, let's say I would have the first tree, and you mentioned, for example, let's see a tree with 3 different levels, right? So let's go here, and let's say I would get here. Now I have these end nodes here, which I'm marking in yellow. So this is where I'm going to make my predictions. And then what I'm going to do here is to see, okay, so how good of a job did I do? So if we have here a variable that is numerical, so let's say I'm going to calculate here my y minus y hat in all of those different nodes. Sebastian, you want to say something?
Yeah, it's basically we're figuring out the residual. What was the error our model is still doing even after training, and then these residuals, this remaining error, that's what we're going to use for the next model in this sequence.
Exactly. So here, the dependent variable of the first tree, you might think of it, this was the y. Now for the next tree, my target's not going to be the y anymore. My target's going to be the y minus y hat. So that for a regression problem, right? So I'm going to grow another tree yet, but that's not focusing on the y anymore. That's focusing on the y minus y hat. So basically on the residuals. So let's say we have a new tree that looks something like that. And then I'm going to repeat this process again. So perhaps I'm going to call this here y hat 1, right? And the next time I'm doing that, then I'm going to get another set of predictions. And then again, I am going to calculate how well of a job am I doing here. And that boils down to calculating, well, my y minus my y hat 1 minus my y hat 2. And hopefully that brings me a little bit closer to the original value. So getting those predictions together, that's gonna actually get me to something a little bit closer. Or in fact, what we can actually think of that is something like, because my objective, yeah, in theory, my objective now is that. So actually that was indeed more intuitive. So I'm going to leave this here. So my y hat again. So because my objective was y minus y hat, y1 hat. So that was my dependent variable and my objective. And this is what I got as predictions. So I want this to be very close to one another. And then we can proceed on this fashion until we get y hat 3, y hat 4, y hat 100. And that's going to hopefully together take me closer. The sum of all of those y hats is going to take me closer to the real y. So that's how we should think of it in the context of a regression. Now, in the context of classification, that's slightly different because we don't work with the idea of residuals. But instead, what we should try to transport as parallel is that whenever I get down here and I see what is my classification error, so that's how we're going to measure this. So we have the classification error. And then with that, we see, okay, so those observations that had an error that I did not predict correctly, they're going to have a higher weight when I'm growing the next tree. So the next tree is going to focus more on predicting these observations. And
because when there was no error, basically our target is the residual of 0 or a very small number. And that's very easy to predict. So the new decision tree will basically figure out, okay, how can we separate the samples where the original model is doing really well from the ones where the original model is doing pretty badly? And how can we improve on those errors that the original model made?
Exactly. That's a very good point. And here, to your follow-up question, so you're asking, okay, so which y hat do we take, or which values do we take? So we take all of them. So if you think like what is the data set that we had in our hands? So let's imagine we had a table here, and let's say in the beginning we had like x1, x2. So these were our dependent variables, and sorry, independent variables, and we go and we had a y. So this column here was our objective for the first tree. Now in the second tree, because we calculated y hat 1 for everyone, because we got the predictions for every single observation. And what are these predictions going to be? It depends on which leaf did this observation fall, right? So let's say, for example, let me use some other colors here. So let's say this here was the green leaf. And let's say this here was the blue leaf. And everybody who landed on the blue leaf is going to have the blue prediction. Everybody who landed on the green is going to have the green. And everybody who landed on the yellow is going to have the yellow. And then in the next step, what I'm going to do is for each of them, I'm going to calculate y minus y hat. And that's going to be the target for the second tree. So that's the first tree. That's going to be the target for the second tree. So this is what I want to predict next time. And we continue doing this. So you imagine we actually do not add new data to the data set, but it would be equivalent to that, to adding a new column and then running again another regression with this new column being our target variable.
And at the end, after we have done this for maybe an ensemble of a couple of trees, I don't know, 3, 4, 5, however many you want, when you then want to use this ensemble, you do not use some sort of majority voting, but instead you run through the entire sequence again. For any new sample, you first run it through the first tree, you get your y hat 1. You also run the same sample through the second tree, you get your y hat 2. And your overall prediction, it's going to be the overall sum of all of those predictions. Basically, it's the original prediction corrected by the second tree, corrected by the third tree, and so on for however many you've got.
Mm-hmm. So in the end, you would have something like the sum of these y hats for all the different trees that you estimated. So a combination of all of these predictions, if we're talking about a numeric variable, right? If we're talking about a classification problem, that's what I think your question is getting at here with the weights, right? Because this idea with the weights, that's applicable to the classification problem. And there you do not initially set any weights. So initially, all the observations are weighted the same when they go through the first tree. And then the model automatically adjusts these weights to go to the subsequent tree, depending on, did I get this observation right or not? So if not, then these weights become higher for the second tree. And let's imagine now we have a very problematic observation here that I still do not get right for classification, even though I have run through 100 trees. So this is going to have the highest weight in my data set, along with whatever observations that also got wrong at the same amount. So the observation that I was always getting wrong for the predictions, this is going to have the highest weight. And then from there you go decreasing according to how many times did I get this observation wrong. But you don't need to set this. This is typically done automatically by the algorithm in the background. I hope that that answers your question. If not, please feel free to follow up. So buenos dias, Rodrigo. And we have another question. Yes.
Which cases do you recommend for the algorithms that we viewed yesterday? And so what did we look at yesterday? Very quick recap. We have looked at decision trees. One variation of those are these conditional inference trees. And we started looking at ensemble methods with this bagging and boosting. And decision trees in general are a very broadly applicable tool that are striking a nice balance between they are powerful enough to model nonlinear relationships, but as long as you're keeping the trees relatively small, they're not super complicated and demand super powerful GPUs to calculate. So I would recommend them for many different sorts of use cases as one of the first models to try after you've exhausted just a normal linear regression or logistic regression. Like I mentioned before, try to start with the simplest model and incrementally get more complicated as you need to be. And so these decision trees are a good early model to try.
That's a very good point. And if you want to get a bit more out of those trees, then using combinations of the trees, a combination of these weak models is typically a very good choice. So that's also very helpful. So that's part of what we're going to discuss today, because yesterday we discussed just very early ideas of how can we combine these models. And today we're going to take a step further and also talk about other ways that we can even improve these results a little bit further. Because if I'm not mistaken, in our configurations in which we did not tune the parameters or just used very standard parameters, the conditional inference trees actually did a better job than bagging and boosting. So what we're going to see today, without wanting to spoil the results, but it could be the case that we can do better than that.
Yes, the methods, if we're just applying plain bagging, there are some shortcomings that the technique for today can deal with in a better way. There was also another question, yes. Specifically, it just came in regarding the drawing that was just on screen. Do the three models on the left side use the same data set? Yes, this was just a description of what presumably you were doing in the approach you described. And what if we are doing an ensemble? We want the models to be different in some way so that they can offset the weaknesses of each other. And one way to do that is to feed them with slightly different data sets so that they, even though you're using the same modeling approach, the results will hopefully be slightly different. But another way to build an ensemble, which we didn't go into much detail, but you can do it, and that's what we can see here. You're feeding different modeling approaches with exactly the same data, but you're using different modeling approaches. So we've got the same data set on the left side for a linear model, for a decision tree, and for a support vector machine. So it's basically a different way of achieving differences in your final trained model so that they can hopefully offset each other.
That's a very, very precise, very relevant point, right? So basically, there's several ways in which you can combine things. So if the only thing that we should keep in mind is if you're using the same data and the same type of method, then we're literally gonna get the same model, right? So for example, if we say we're gonna use a tree with and we're gonna run three trees, but with the exact same data, then we're just gonna have the same thing all over again, right? So as Sebastian mentioned, either you can use the same data, but use different types of models, or you can use slightly different versions of the data. So while Sebastian was explaining it, I tried to make it here visually, try to accompany, to follow his explanation with that. So basically what we have here, so imagine we have a data set in which you have 3 observations, one red, one yellow, one blue. So generating slightly different versions of the data set here would mean that we take bootstrap samples. So that's what we did with bagging. And we just change something small in the data set. So for example, here in the first one, the blue observation is not there, but we still have to keep the same data set size. So then we have 2 times the red. Then in the next one, the red does not appear, but we have 2 times the yellow. And in the third one, the yellow does not appear, but we have 2 times the blue. So that's what we do when we're doing bagging. So we perturb the data set slightly, and with that, we can use the same method, but with slightly different versions of the data. So we have that one. And we had another question here also about the concept of surrogates and split variables. All right, so let me start here, perhaps from scratch. So we have a clean slate.
Yes.
Then, yes. Let me go here. So the idea here is when we're doing these splits. So imagine I started a tree and I say, okay, so we're going to split here, for example, on did the person show proof of income, yes or no, right? And what happens in some cases, this variable might be missing for a couple of observations. And in regression, what would happen is that this observation would just be kicked out. We could not estimate anything for that with missing data. Now, what happens in the trees is that if you're using surrogate variables, is that whenever I'm calculating this split here, so I'm saying, okay, so here, let's say in proof, yes or no, the tree also calculates what are other variables that I could have used here that would give me a very similar result, meaning the same observations that I have that are going to the left and to the right. I have a very similar number of actually the very same observations are being sent left and being sent right. That would be the perfect surrogate variable, right? So if you say, well, I do not have proof of income, yes or no. Perhaps I have another variable that says, for example, let's say maybe how high is my income. So let's say this could be our next variable. And if I use this variable, let's say, I don't know, maybe let's imagine some scenario here. If the income is larger than 1,000, then people typically will show proof. If not, they are probably not going to show proof. So let's say something like that. So if I would, maybe I would use this split here. And if it would send the exact same observations to the left and to the right, this would be a perfect surrogate variable. So whenever we do not have this observation, this variable here being filled. So if this is missing, I will use this one. Now, it's very hard to have a variable that does exactly the same split. So typically you're going to have some overlap, but it's not going to be very perfect. But it's the next best opportunity to make a split whenever this observation has a missing in the variable that we would actually have needed here for the split.
And thank you.
The main the thing is, this is it's finding a surrogate split for every possible node in the tree, even if during the training data there was no missing values, because we cannot expect the same level of data quality for all time. Maybe there will be some missing values in the unseen data sets that we use to test the model. And that's when the surrogate splits would also come into play. So that's why it's determining some surrogate split for everything to replicate the same result, even if some values are missing.
That's very, very good point. And whenever these perhaps we also going to encounter some cases that where not only the main variable is missing, but also the first surrogate. So you would go then to the next best option. So typically we want to calculate at least 2 or 3 different surrogates for each split, so that we always have some fallback options whenever the first surrogate is also missing. So this could also happen in reality. Right now we have here, so Raul was also complementing what he told us about the models that he used. So it was 3 different methods using the same data set. All right, so that's exactly what we have we had in our drawing, except that was not a new network or a dictionary approach, which is but it's 3 different models, but based on the same data. Thank you for this additional information.
And we also got the question, the surrogate variable is similar as the instrumental variable approach in regression. And if I understand that method correctly, some variables that would be really useful for us might be costly or difficult to obtain in real life. So we try to find some sort of instrumental surrogate variable that is very, very closely related to the actual term that we are interested in. So in that sense, yes, this is very similar. We would ideally want to use the original primary split that our analysis showed is the ideal splitting point at this time. But if that's not available, we will then defer to the surrogate. So in this case, the algorithm is doing this instead of us making a decision, but the idea is very similar, actually, yes.
It's kind of close in a sense that we're looking at a variable that has at least a strong correlation with the variable that we would like to have, but that is missing in this situation, right? So that's something that we also want an IV, an instrumental variable, to have, because to be a good instrument, it must have a high correlation with the original variable that we have in our hands. Now, just with the terminology, the surrogate would be very close to a proxy. So because a proxy variable is a variable that kicks in that we would use whenever we do not have that variable available. So we say, okay, I would actually want to have that, but I do not observe that. So the next best thing that I observed that I could use in my regression, for example, so in the regression framework, is this variable here. So we would use this as a proxy. Now the only so the terminology, the only difference related to the instrumental variable is that in an instrumental variable approach, you typically use an instrument when you cannot use the original variable. You have it, but you cannot use it because this variable is endogenous. So you want to have an instrument that you can use in the place of this variable that is perhaps assigned randomly, right? So you're going to use this variable as an instrument for the original variable, but as Sebastian said, one precondition for that is that they're both highly correlated, right? So that this when I'm using this instrument in predicting the original variable, that I have a very high R square there. So that's only just to make that point. So it's a similar idea, but we're not using this with the purpose of substituting an endogenous variable, but the same principle applies. So they must be very highly correlated, but very
more direction. They need to result in the same split at the end. That's what it's looking at.
Mm-hmm. And we also have another question from William. So William is asking, is it better to use bagging and boosting with a big data set and multiple characteristics? Well, with bagging, it's actually an artificial way of generating new subsamples of your data sets, or at least slightly perturbed whenever you do not have the luxury of saying, well, I have so much data that I could just split into several different samples and let one model run in each of those, right? So that's actually a method that you could definitely use whenever you don't have so much data available. Now with boosting, what can happen is if you have a small data set with many different variables, and you are letting the boosting run many trees one after the other, you might run a risk of overfitting there a little bit fast. So if you have many features and you have a rather small data set, ideally you should try not to let this model run all ad eternum and becoming very big. But I would say in principle, both methods are applied also when you don't have lots of data, because the decision that you're doing in each tree is n observations against 1p, so one variable at each time. So that's why they do not fail when you have small n and large p.
Yeah, I quite agree. Basically, bagging is a way to artificially inflate your data in a sense, and boosting is trying to exploit the very last bit of a weak model.
Sorry, Hector, you unmuted yourself. Do you have a question? Okay, I think that was a mistake.
Yeah. Anyway, I think that was all the questions that are. Oh, can we use bagging with time series?
Can I use bagging with time series? I mean, you can, but then actually, I would go with another concern first. So in these methods that we're discussing here, in the way that they're originally conceived, you do not preserve the structure of a time series, right? So you have that issue there. So we're thinking here in the cross-section world. Now, if you want to preserve this time series character of your data, you would, at the minimum, a bare minimum, need to create additional columns on your data set to say, for example, my value of y depends on x1t and x1t minus 1, x1t minus 2, perhaps yt minus 1, yt minus 2. So if you would want to have something like in the spirit of an autoregressive approach, you would first need to create those columns there. Once you do that, and then the big assumption here is that those units that you have, so the observations, they must be independent from one another. Then you can say, okay, I'm going to train this, for example, for a data that has this kind of time series structure, and I'm going to generate additional samples by bagging this data set. But this comes with a grain of salt, because these models, without further manipulation, they are not plug and play for a time series. And I don't know, Sebastian, maybe you see it differently.
definitely a non-standard approach. Maybe you could drop some of your entries from the time series and drop several different ones for each of your trees in the bag. It's not something that is very commonly done. I would maybe advise doing some research if anybody else has done that before, but maybe another technique would be better used for creating a method in that case.
Because this structure is not preserved, right? So that's one important point there. And we have also an additional question in the Q&A from Slido. Are there any cases or characteristics in the data set which is not recommended to use decision trees? I wouldn't say there's anything that would be a no-go. I mean, if they can handle numeric data, they can handle categorical data. So the types of data that you can put in there, I would say it's quite flexible. Sometimes you have restrictions in the implementation of the packages, right? So as we have seen yesterday, for example, the conditional inference trees, that this implementation in R, it does not allow you to give a categorical variable that has more than 30 categories. Because of the way it does this permutation test, it would be computationally very, very expensive. So it says, hey, buddy, stop there, more than 30 categories, I'm not gonna do. It's not because it's theoretically it's totally possible, it's just because it would take too long to compute. So it stops you there. But other than those restrictions because of computational issues, typically there's nothing that that you couldn't give it, I would say.
Some of those examples of maybe an artificial situation when a decision tree might not be doing also well was something we showed in the slides, I think on Monday. For example, when there's a strong crossover interaction. Since this is a greedy algorithm, it's only looking at the very current moment and it's trying to get a split right now. But if a perfect split would require immediate interaction between two variables, because if one is big, then the variable will have the opposite correlation with the other one, so they are really dependent on each other. In that case, decision tree will not do so well. However, it might be difficult to know that beforehand. So give it a try and see how well it's doing. That's why we are preparing cross-validation or this training validation loop.
Yeah, typically you would not, in a real setting, you would not know the ground truth. So what you should always do, and this is something that we forego here during this course, because that makes up to most of the time when you're dealing with data. So we do not have time for a session on feature engineering, but that's what you should definitely work on before you start trying different methods, right? So in the case as Sebastian mentioned, for example, we would not know a priori whether this is present or not. So we should try to also give the model some features that we generated out of the features that we have in the data. And if those appear in one of those first splits, then this is partly then something that is relevant to make the predictions, right? And this is something that we would not know a priori, so we just need to try it out. And if you generate all of those different features and they never picked up for a split, then this would at least suggest that these relationships are not there. All right. I think we do not have any further questions.
Not at the moment.
We do. So there's so there's one that just came up here. So Maria just asked here in the direct message. So let me perhaps copy it. So from a technical point of view, she's asking, is it similar to run these models on R and Python? Most of the times, yes. So most of the times the implementations is just the same. Sometimes they offer you a couple more possibilities to tune this or that, but most of the times you're just faced with very similar results.
Particularly if you're using some of the very highly optimized models that are using really all the available parallelization and optimization tricks that the community has been able to come up with. those highly optimized libraries are commonly written in yet another language, like C or C++. And in that case, you can call this common library both from R and from Python. So in some highly optimized models, it might be literally the same code that you're running.
Very, very good point. Yes. So in the end, you're just using the same solution, but you don't see it in the background. Yeah. Very, very good comment, Sebastian. All right. Now another question we have here in the Q&A. Can you remind me where can I find the presentations? So our slides are in the RStudio cloud. So when you open your project, you're going to see it there in within the files, and we're going to send them around also to Gerardo and to Laura, and they're going to share them with you so that you also have them afterwards. I think in the official page of the course, right, Gerardo? Yes. Mm-hmm.
Yeah.
All right.
Correct.
Thank you. So, if we do not have any further open questions, and I think this was a great discussion. So thanks everybody for the great comments and the great questions. I think that's very, very helpful also to all others who perhaps have similar questions. So to really get this these concepts, because they are very important also for what we're going to discuss today. So our topic for today is we're going to continue working on the ensemble methods, and specifically we're going to talk about two or actually three different extensions of what we have discussed yesterday. So the first extension here is with with a random forest. Okay, actually you can use this for regression, but we're going to keep talking about it in the case of classification problems. And after that, another extension of it. And finally, after the break, we're going to discuss gradient boosting, which is yet an extension of the boosting method that we discussed yesterday. And here, just a short recap. We discussed part of it also during your questions. But what we want to do when we're combining different models is we want to take these models that alone are not so strong. So basically, they have a high bias, right? So because alone, they're not very powerful. But if we combine many of them together, then we actually trying to move here towards the sweet spot where combining them, these models that they must have slightly different predictions, then we can actually get stronger predictions by combining those together. And by doing that, we also avoid that we just have this one single model that made a wrong turn somewhere, and that this is going to be our final prediction, right? So you avoid overfitting your data, and we want to make sure that we land somewhere here and not there where, if we're going up this curve here, we're basically having a small bias in the training data. So we're memorizing the training data, but as soon as we apply it to new data that the model did not see yet, it's a fiasco. So we want to avoid that. And that's one of the ways that we can accomplish this. Then what we have also discussed, so first we talked about a bagging, right? And that was the idea that we discussed now during your questions. So just to say, we take the original data set and make slight changes to it. We keep the same size of the data, but for that, we're going to repeat a few observations here so that in the end, we have the same size, but these data sets are slightly different than the original one, so that we can then use them to train different models and get slightly different results. But as we have seen yesterday, this still leads us to having quite similar trees. So you might remember that when we compare the results of the card tree, so coming from the rpart library, which is basically just card, they cannot call it card because it's a trademark, so they just call it rpart, but it's just basically card trees. When we compared that with bagging the trees, then we saw that actually the results were even a little bit worse because we were just repeating the same mistakes that the previous tree did, or the previous trees did. So in a sense, just doing that was still not enough to get something very, very strong. So the next question is then, how can we improve on that, right? So besides adding some randomness here in these rows of the data set, but not giving the different models the same data, what can we do on top of that to try to improve this? And then this boils down actually to what is the problem that our bag trees had in the first place. And the problem that they typically have is, if you would take the time to inspect those different trees that we grew, is that they mostly have the same splits, at least in the beginning of the tree. So they identify a couple of variables that seem to play an important role there. And then the first 2 or 3 levels, most of the times they're exactly the same. So then afterwards, because of this randomness in the rows, the trees start to split on different variables, but this big important chunk in the beginning is typically the same, because we allowed all of these models to see the same columns here. So they're seeing all the same variables. They're just seeing slightly different version of the observation. So meaning some observations are in, some are out. So we added here some variation, so some randomness, but the columns, they're all the same. And that results in very similar splits, and therefore also very similar predictions. So the idea here with random forests, how does it improve on the idea of bagging? There, we're not only having randomness here, but we also add randomness in the columns of the data set, so in both dimensions. And the way we do that is that we do not allow the tree to see all the variables at once. So what we do is we introduce also randomness in these columns by saying, instead of letting the tree see the whole data set, so let me go back here. Let's say for the first split, I say, well, the tree is only randomly going to be able to see 3 of the 6 variables here. So I just cut this out here for the first split. And then for the second split, maybe I say, okay, now it can see those 3, but these other 3 here are not shown. So I'm letting the tree have the opportunity to learn whether there are other variables that could have played a role in the model if these very strong variables were not there in the first place. So that leads me to having slightly different predictions there, okay? And perhaps let me show you here that in another picture that I think makes things a little bit clearer. So imagine, again, you have this data set here. So this is where we started from. And what we're going to do differently this time is we do the bootstraps. So meaning some of these observations are in, some of them are out. And this happens here for each of those samples here. Now, the next step is when I'm going to do a split, I do not show the tree everything that I have in my hands. Instead, I show a random subset of these variables. That's what we call the M or M try in most of the packages that are implementing random forests. And there's a rule of thumb there. So typically you would say you're going to go with the square root of the number of variables that you have in a data set. But in practice, this is something that you're going to find out. So you have to tune these parameters and try different values of the M try, and then see which one does the better job for your data. So for some data sets, it can be that you go a little bit higher than the square root of the number of variables. For some of them, it can be that you go a little bit lower than that. So this is something that is just the square root is just a rule of thumb. So you definitely need to try it out. But the idea here is to say, okay, so imagine I have a very strong variable that when I was bagging the tree, all the trees started splitting on this one. Now, when I'm using this trick of adding the randomness in the columns, maybe in some of those splits here, because this is done at every single split, sometimes this variable is available, but sometimes it's not. Sometimes the tree is only going to see a random subset of these variables, and this one is here is not included. So I'm giving the tree the chance to start, for example, with this variable here. And the same thing happens at every other split here that I have in the tree. So in the end, that leads to trees that are much more different from each other than we originally had before. And let's take some time to let that sink in, because I think that's one concept that is very, very important, and especially this distinction between the bootstrapping and random forest. Because again, before we had randomness only here. Now we had randomness in both dimensions of the data set. And that's actually the real trick here, why random forests are so popular and so strong, because really improve quite a lot on the predictions that you would have from a single tree or from bagging the trees, especially in the case when you have very strong variables in there.
Like we mentioned before, with most ensemble methods, we're trying to get some variation between all of those different models in our ensemble. And if you remember, or if you've tried playing around with the code yourself, pretty much all of the decision trees that we created so far, they all picked up on the exact same variable to use for their first split. And by disallowing some of our models in the ensemble to do that, we're forcing them to literally have a different structure than the rest of the trees in our forest. And that's exactly what we're aiming for, having a different structure.
Exactly. That allows you to uncover new patterns, new relationships, because you're giving the tree the chance to see some new things, right? So that's the whole point here in the end. And again, how are you going to set this threshold? So what share of the total number of columns or total number of independent variables that you have or features that you have in your data? So that's something that you're going to choose. So you have to find out by trial and error, basically there. And if you set this number to the number of features that you have in the data, then you just back to bagging, right? So if you let the data set see all the variables that you have available, then you're just doing bagging, meaning you're just doing this randomization on, you're including this randomness in the rows, but not in the columns anymore, right? So you can also try it out if you would like. So when you're running random forest, so that algorithm is a little bit faster. So if you run it and you set the mtry to be exactly the same number of variables that you have in the data, except for the target variable, then it's going to give you literally the same results. All right, now what happens here, which is also something quite nice. So in their paper, where we originally have the concept of random forest, they also discuss at length one very nice property of the forest, which is because we are running, so every tree is grown using a bootstrapped sample of the data, original data set. It means that by definition, I'm always going to have a few observations that I did not use to grow this tree. So imagine here, if I say, well, this is my original data set, and let's say in one bootstrap, the gray observation was not there, because it was when I randomly picked some of those observations to be in the new data. Sorry, Alba, was that a mistake, or do you want to ask something?
Sorry.
Oh, no worries. So if we do not have this observation here in the bootstrap that I use, for example, to grow my tree number 1, it means that I can use this observation to have an estimate of the error that my model has, because this observation was not used to train the model, right? So I have here, in a sense, a very nice property that I can use this as a validation set for this tree, because this observation was not used in growing this tree. And the same thing happens for every other tree that I'm using. Some of the observations were just simply not in the data that I used to grow this tree, because they were not part of the bootstrap sample that was used in the growing process. So I can use them to have an estimate of what would be my generalization error. And what do we call these observations? They're called, in a context of random forest, we call them out-of-bag observations. So whenever you're using those methods, or you're reading something about them, and you read, oh, this is the out-of-bag error, this is nothing more than the error that you're measuring, so they're estimating the generalization error using the observations that were not part of growing each specific tree. Okay, so that's also a very nice property here that the random forest explore. We could also have done this with bagging as well, right? So nothing would have prevented us from doing that, because the same property applies there. But typically the packages that implement bagging do not offer this feature, but the packages that implement random forest, because this is also in the random forest paper, they do implement this. So they use this nice feature. And Typically, by default, what you have in the algorithm, if you do not say that you wanted to have this share of observations differently, what it does is that by construction, in a standard setup, it will take 1/3 of the observations to be set aside, and each of these bootstrap samples has approximately 2/3 of the original observations, meaning 1/3 is just made of repeated observations in there. Okay.
Basically, this is another way of doing cross-validation in a sense, just specifically tuned for random forests in a way that automatically gives us some additional measures.
Yes, that's a very good point. With the observation that you're doing this one time for each tree, but we could also make things even funnier and more complicated by doing cross-validation on top of that.
We can mix and match the tools however we want.
Exactly. That's a very good point. And because these observations, they were not used to train the model, this is typically also what the packages will do when you ask for a measure of variable importance. They will compute this using the out-of-bag observations, right? And that's something that's also important there. And another thing that I think we also mentioned this later on in the slides, but just in case we don't, you can choose among two types of variable importance measures in random forests. There's one that is based on the Gini index, and there's one that is based on permutation tests. You should prefer the one that is based on the permutation test, because as we have discussed yesterday, the splits on the Gini index, they tend to be biased. One towards variables that have a large number of missings, and two variables that have a lot of different values. So for example, categorical variables with many, many different values. So to avoid that your importance measure is somehow biased by that, you should use the permutation-based measure, which is doing something in the same spirit as the conditional inference trees are doing. All right. Now, any questions about that so far? Or is this concept, and especially the difference between random forest and bagging, clear to everyone? All right. I don't see any questions coming in so far. So these are the parameters that we will typically tune when we are working with random forests. So we have the number of trees, so meaning how many models we want to estimate. We have the mtry, which is what is the number of random, the number of variables that we randomly pick and let each split see. And this is a decision that happens at every split. Okay, so it's important to remember that. So it's not that I say, oh, I'm going to let this tree see these 10 variables, and it's going to be always like that. No, at every single split, it's going to see a slightly different subset of the variables. So this time it's these 10 variables. The next time is another subset with 10 variables. So the size is the same, but the variables that are going to appear there, they can be different at each split because you're sampling every time new. Okay. And the node size is something that we typically also want to tune, is what is the minimum number of observations that we want to have in a leaf node. So that's very similar also to the measures that we have seen yesterday. And there's quite a lot more there. So these are the ones that we're typically going to play around with, but there are many more factors that we could also tune there and change, as we're going to see when we go through the code. And here, just one first glance at how our results look like. So we see from the random forests implementation, and again, this is not tuning any hyperparameters. So this is just us using very standard configuration. We see that it does quite a good job. So even though it doesn't get very close to the C tree, it actually does a fairly good job. So on the precision, we're also there. But again, we might be a little bit more concerned with our recall. And there, it's better than the boosted trees, and also better than the bag trees, because the boosted trees were better than the bag trees. So by construction, the random forests here with this standard configuration were better than the bag trees. But it's still not getting right there in comparison to the conditional inference trees. But again, keep in mind, we did not do tuning in any of those different models. So perhaps random forest could get something more out of it after we have tuned it. but we see already that there's quite a substantial improvement here. All right. And perhaps also important to say, these trees here, they do not suffer from the bias in the splits. And that can make quite a difference if we have a data set that either has lots of missings, which is not our case, or a data set that has many variables with a high number of features with a high number of values. And that we actually have. We have many categorical variables that have several levels. Some of those we even had to cut out because they had more than 30 levels. So this is something that could be playing a role here also in this difference that we see. And Madeleina's asking a question.
Why is the no default so small compared to other methods in the random forest? So she's referring to the confusion matrix. In the random forest, there was a very small number of false positives. There were only 7 instances where we, for the random forest, predicted a default, but it was actually not a default. Even in the decision tree model, which overall mostly has better performance matrices, that specific type of error was 10 times as prevalent. And that's really hard to say. It's just mostly something that happened. I don't think there's any good way to explain that. That's where we are getting into interpretability issues.
So why was this rate of false positives or the rate of false negatives, why did it behave the way it did? That's something that with these black box models is quite hard to know. So you could say, okay, so the intuition is the model performed a better job in classifying this class or that class better, but why? That's a question, again, as Sebastian said, it's something that we can only answer if we're also docking some of the explainability methods that are available out there to really glance into the results.
I think one way to think about it is that the way the models were trained so far, we didn't put any particular weight on the different classes. The false positive was just as bad as a false negative during training. And looking at the false negative rate, that was 4 orders of magnitude higher with 2,400. So basically, this difference between 7 and 70, that's just within the random distribution. I guess it's insignificant compared to the error that we've got from the false negatives. So that's why it's not that surprising that there's such a high variation when we're just looking at these 2 numbers.
And this is what is actually harder to predict. Right, so that's actually where our model has less chances to learn from the data, because we simply have less possibilities of learning from it, right? So this makes up to 20% of the data. So in a sense, we give the model a fair chance to learn from this, but not so much from this because of the imbalance that we have. Yeah, that's a very good point. So Maria is also asking something here. So she says, in the example of this slide, logistic regression, which is easy to understand, perform the same results in accuracy, precision, etc., to random forest, which is more black box. Is that right? Absolutely. I mean, when you have a logistic regression or any type of regression, you can interpret the coefficients most of the times directly. So there are a couple of exceptions when you have to do some transformations, but most of the times you can actually interpret those coefficients directly. And in that case, okay, so with logistics, for example, we have to transform things to odds ratio or similar transformations, but overall we can interpret them directly. Then as we're moving towards here, we're giving these models some kind of black box character, right? So it's a little bit harder to see what they're doing, especially here. If we have a fairly small tree, you can still visualize the tree, see what's happening. But as we start combining many trees, things do not become so straightforward anymore. even if you would be able to see all the 100 or 500 trees that you grew, how would you combine them into understanding how would that make up a single prediction? That's something hard to do. And that's why for that, we really need those methods that try to shed light into what's happening. So try to understand, okay, you just use some mathematical tricks to try to see what happens with my predictions. If I change my variable like this or like that, if I increase my variable, the value of this variable, or change the class of this variable, what happens with my predictions? And we can even take this further to say, okay, we don't leave the other variables in their averages, but actually also compute this for all the possible values of the other variables. So these are just a couple of mathematical tricks that we can do to try to infer what is the influence of a variable in the predictions. But beware, it does not mean that we are measuring the effect of the variables on the y. It's on the y hat, right? So according to our model, what these methods do is they try to help you understand what is the influence of these variables on the predictions, but it does not give you any glance of what would be the real effect. Sometimes there's no effect. This is maybe good predictors, but they have no causal effect on the variable that you're interested in.
Furthermore, something you need to consider is in tendency on this slide, the further we go to the right, the more hyperparameters these models have. So it's hard to objectively say, was this the best random forest that we could have used? Maybe we should have made the trees deeper and longer, and maybe we should have allowed it to run further. Maybe that definitely runs the risk of overfitting and making the performance on unseen data worse. But maybe we didn't reach that point yet. So it's hard to objectively say what is the performance of the random forest model on this data set. Well, which random forest? This is just basically one sample of a random forest.
Yes. So to summarize, so what we find from these models is that we can actually get some good predictions out of that. But on the other hand, because sometimes we're not giving important variables the opportunity to show up in all the splits, because we just omit them sometimes when you're doing this random sampling of the variables that we're going to let the tree use at each split, we might end up with trees that are slightly biased. So meaning their predictions are not exactly on the point which we wanted to achieve, but instead they deviate more from the original values. But this is not something in principle that is always bad, because we actually want to make sure that these models are also generalizable, right? So if we would have predictions that were very, very perfect on the training data, we might run the issue of overfitting. So in a sense, we are most of the times willing to take up some bias so that we can make these models more generalizable to new data that it did not see yet. But again, as we have just discussed, and for that was a very great question, Maria, that in that case they also become a little bit harder to interpret. So looking at the model alone does not really give you much insight on what happened actually there. So we need some other methods to help us with it. And as Sebastian also mentioned, so this is just basically what he said before. So we have to tune these hyperparameters. We have to search for different combinations, because just having one tree with one combination does not mean that that's the best possible result that we could get. And that applies to all of those models that we're discussing here. So we should always go and try to search for these combinations of parameters that can, so that I can at least have an idea, is this the best possible thing that I can get, or can it even become better after I tune these parameters? Now, I mentioned before that we should be careful also when using these interpretability methods, because having a feeling about how does a variable impact our prediction does not necessarily mean that this variable actually has a causal effect, right? And we're going to discuss in a second. I see Fabio has a question here. So let's take his question first. So he's asking, so maybe I'm getting ahead of the course content, but taking advantage that we're talking about parameters at some point, working with the implementation of our random forest in R, I know that there's the parameter of weights. At the time, I interpreted it as the proportion of records associated with each category of the response variable. And I just calculated as a number of records associated with the category 0, 1 total records and assigned that value in the variable and indicated in the algorithm. However, I would like to know if my interpretation is correct. So let me do the following. So, and that's something that is quite interesting to whenever you're starting to use a new method or working with a new package, we can definitely go into let me go here, stop that. We can definitely go into the help of the package and see what are the specific, let me go here, random forest, what are the specific parameters that we can use and what do they mean? So let's go here. So it can do this in R always by using a question mark and using the name of the package or the name of the function directly if you have loaded the packages already. So in this case here, it's quite convenient because I already loaded things before. And the package has the same name as the function that we use. So also random forest. So you said you were trying with the weights. So let me go here. So I don't see a parameter here that is called weight. So perhaps
weights. Yeah? It should be called weights.
Yes, but still it should have been, it should show here. So I'm seeing here, these are the parameters. So we have max try, we have replace, we have sample size, node size, maximum node, importance, proximity, etc., etc., etc. So we, in principle, there's no explicit parameter here with weights.
Which package are you looking at? Because I'm looking at it at an R documentation where there is a weights parameter.
I'm using the random forest package. Perhaps is it a matter of the version? Perhaps this is something new that they included. Yeah, it could be the case. So what version do you have?
I'm looking at the 4.7 documentation.
Okay, so that explains things. So let me do the following. So probably Fabio is also using that version. So I'm going to stop it here. So perhaps you can share your screen and we can go through the documentation there together.
So let me share my screen. What I did is I basically just Googled it to find the package. And there is a very good website, rdocumentation.org. There you can, independently of what package you're using, get a very recent documentation for it. And in this case, yes, there is a weights parameter for the random forest model. So let's check it out, what it means. A vector of the same length as our samples that are positive weights used only in sampling data to grow each tree, not used in any other calculation. So when it is drawing random samples from our overall data set to build each tree, it's not drawing them with equal probability, but some of these samples have a greater weight than the others if we are passing this optional parameter. Basically, it's a way of saying some of these samples we really care about more than others.
And in that sense, then you shouldn't use it as the proportion of the records necessarily, but perhaps let's give an example. So imagine you have a data set with several institutions and you want to model something and predict something for them. Perhaps you know already from your domain knowledge that some of these institutions behave very differently. Perhaps they represent very large institutions or institutions that have certain characteristics, and you want to make sure that they are always or with a high probability they are in those data sets that you generate artificially. So you do not want all of them to be kicked out in one of those bootstrap samples. So what you could do is you could give them a higher weight or even the highest possible weight to make sure that they will show up always or with a very high probability in all those bootstraps. So you ensure that that your models are always also learning from these observations. But this is something that you should use with care, right? Because imagine that for some reason these observations have a very, very specific behavior, then perhaps your model would learn this, let's say, memorize this, And perhaps this is also something that is not generalizable to other samples that you would see from the same group of observations, if you will. So this is something that you should use with care, but definitely a valid approach. If you say, as Sebastian mentioned, you definitely want to make sure that these variables will, these observations will appear in a sample, or at least they will appear with a high likelihood. But good question there. And I see that I need to update my random forest.
That's definitely a very good general lesson as well. Oftentimes, all of these different packages, they're giving us so many tools and so many options. You really should try to get comfortable reading the documentation and just like learning to read a paper, how to get the most relevant information to you as quickly as possible is really helpful to be able to get the information that you need from package documentation as quickly as possible.
Definitely. And you're going to recognize that as we go towards more and more complex methods, the number of parameters that are there, some of them are optional, some of them are mandatory, but always come with a standard value. But you're going to see that this list only gets bigger. So definitely take the time to take a look at them and see what do they mean, what are the possibilities there, because we only include in the slides a very tiny subsample of all the possibilities that you can play around with there.
And we've got a related question. So could we use the weights parameter to balance the sample and have the same quantities of defaults as non-defaults? What would be the consequence of doing that? It wouldn't necessarily be the same quantities of defaults as non-defaults, but the tree would definitely behave as if there were. It would, in essence, care more about the default situations. So what we would expect is that it gets better performance on those samples. It produces fewer errors on the default cases, probably at the expense of a worse performance on the more prevalent non-default cases. Maybe that's a trade-off that we're willing to take. Maybe that's just something we need to try out. It's hard to say what would be the impact on some aggregate measure like the F1 score, which cares both about false positives and false negatives. Intuitively, I would think probably the F1 score would get worse, but because it's just not globally optimizing independent of the weights anymore. But maybe that's acceptable to us because we just care about the default situations so much.
Yeah, so in a sense, that would be equivalent. So you could, in theory, construct the weights mathematically so that you have exactly or very close to half of the samples, right? Or some share, so that you have a lot more of the default cases appearing in relation to the non-default cases. But we have to keep in mind this is not really new data. So this would mean you would just repeat. Let's say we have one observation number 1 is a default, and when we include the weights like that, then observation 1 would perhaps show up many times in this data set, because the data set will keep the same number of rows, right? So in the end, we repeating these non-default these default observations many times, if we give them a higher weight such that we change the proportion of defaults and non-defaults in the bootstrap samples. So that would be equivalent to oversampling the minority class here, the default class. Another thing that you could do, and then you would do it actually before you start running your models, is to say, if you have enough data, what you would do if your class unbalance problem is very bad, is to undersample the majority class. So you say, okay, I have, let's say, 1% of frauds and 99% of non-fraud. So you can also say a random sample, a fraction of these non-frauds, and reduce it so that my relationship is now 199 anymore, so that my relationship is somewhere a little bit closer. So you don't want to make this very extreme, otherwise it would throw lots of data away. But this is something that we sometimes do. But typically we do this during training, but not in the test or the validation set. because you want to make sure that you're testing your model with the real conditions that you have in production or in the data that you want to analyze. So you would do this to help the model to learn the relationships in a more fair way towards the classes, but analyze or see the results. You definitely want to do this with the real relationships that you observe in reality.
Yeah, very good point. Whenever you're estimating the performance of your model, when you're testing it on unseen data, then there's no point in shifting the weights anymore, because that's equivalent to just lying yourself and hoping that in the future there are more defaults than there actually will be. That's what the different performance metrics are designed for, to give you information about class unbalances. That's why we have so many different ones. So there's no need and no benefit for shifting the weights during testing.
Yes, very good point, and very pertinent question. Thank you. Now, coming to another extension of random forest. So we talked about, okay, so how do random forests compare to bagging? What are the improvements that we get there? But we can actually take things a little bit further, and that's part of the work of Vaga and Susan Athey, Stefan Vaga and Susan Athey. So they have been working on this for quite a lot of time, and things have evolved a lot, let's say, in the past 5 or 6 years. So it's quite a nice development here that we're seeing coming more and more to the machine learning community, which is basically how can we add all these nice properties and all the strength of those methods to also do causal inference, right? Because until now, we were just talking about predictions. So we want to predict who is going to buy something, who is going to default, perhaps which institution is going to be in a difficult position. But we did not say until now, why is this happening? Or perhaps what is the effect that we measure here from a certain treatment. So far we were not able to do that, right? So we're just talking about correlations, and we are using variables that perhaps give us a signal, a strong signal to predict something, but it does not mean that this effect is causal whatsoever, right? Now, this is here a movement that I really appreciate, because that tries finally to bring both worlds together. And the basic idea is, how can we use the strength of trees and also in the extension of random forests to make this kind of inference there, right? And the first thing that we should keep in mind is that we need to make some adjustments here. So in the first idea of or at least in the original idea of random forest, we really tune our model and use a target variable, the y, so the variable that we want to predict. So we actually have to make some changes there. But what I'm taking a look at here, I think we're coming close to our break, right? So I think, Gerardo, if I'm not mistaken, our break is scheduled to 5, right?
I believe we have our break at 10:30, right?
Yeah, half an hour.
Yeah.
Oh, in half an hour. Oh,
Yeah.
yeah. Okay, great. So, so we still have some time to discuss it before the break. Okay, that's great. So, in that case, and let's continue. So, the first thing that we have to keep in mind is, what do we do with the traditional random forest? So we have a target variable, a y, and we have some features in our data, and we are deciding on those splits in the same fashion as we did with the single tree. So we look at the observations that I have here, and we search through the variables that I have available and the different values that I could use to split on them. For example, is this category this one, yes or no? Is the loan payment amount higher or equal than a certain value? And we try this for all different values and see which split gives me the most homogeneous results in the nodes that are going to come out of it, right? So in a sense, I'm optimizing for reducing the prediction error, right? That's what we have been doing so far. Now, to take this to the next level and to try to estimate causal effects of a certain treatment, we need to make some adjustments, which we're going to discuss now in a bit. But just to go and make a little recap on what do we care about when we're talking about causal inference. So basically, we want to understand what is the impact of a certain policy decision, perhaps of a new law, or maybe we want to know, well, if we give this kind of incentive to certain institutions, or if we treat these institutions in a different way, what is the effect that we get? So does this actually move things towards the direction that we are hoping to achieve? Or does the effect perhaps backlash, or do we have some unintended consequences perhaps of these decisions that we're making, right? And that applies basically to any field of research and activity. And especially if we consider now all the recent crises that we had and all the different policy decisions that central banks were faced with, that's a very, very important issue for us, right? So what are the decisions that we are making, or perhaps now very, very current topic also everywhere in the world. So we are increasing interest rates. What happens with with all the affected parties? So these are kind of really relevant question for us. And until now, or until these methods were developed, machine learning didn't really have a say on this, right? And that's something that is changed here. And the overall problem that we always have with causal inference is that in the ideal world, we would observe the same entity or the same person once receiving the treatment and once not receiving the treatment. So we would have a parallel reality, one in which, for example, this institution was affected by the law, and one in which this institution was not affected by the law. And then we would compare the results and see what was the effect of the law on this institution. But by definition, we do not have these clones, or we do not have these alternative realities out there. So we only observe either the institution was affected or the institution was not affected, but not both. So that's the root of the conundrum that we have with causal inference. And there's, in principle, no direct solution to that. So I'm not going to observe the same entity in both states. I'm only going to observe one of those states. So what is the next best option? So what we try to do is we try to infer these effects and infer this counterfactual by trying to see, okay, so how could I make a measurement out of different individuals or out of different entities that are very similar to one another, and that in the best of the cases got this treatment randomly assigned to them. So I have two institutions that are very similar to one another in several control characteristics. And the only difference is that I randomly said, you're going to get the treatment, you're not going to get the treatment. So that's very easy to understand, for example, in the context of perhaps a medical treatment, right? Some people get the real medicine, some other people get placebo medicine. And we see, okay, how does the effect relate to both of them? So some people are perhaps going to get better even though they got the placebo. Some people perhaps are going to get worse even though they got the medicine. And overall, we're working with these average effects in both groups, as long as they're comparable. And we use this as an approximation of the effect on each person. And the same goes for entities or whatever units of observations that we have. So that's what we know from traditional econometrics, right? And that's the same thing applies here. So we have all these assumptions that we have to fulfill. So the treatment of one unit should not affect the treatment of the other unit. We have also the other many different assumptions that we have out there. So we want to make sure that we have also enough support on the treatment. There are also many more that very well documented in the book from Imbens. So that's a must read for causal inference. But just to cut this part short here, that's what we know from causal inference, right? So just a small recap on that. And we want to make sure that all these assumptions there are fulfilled, which is in practice something very hard to do. So more often than not, we're caught up in a conundrum and we're trying to make selection on observables. And we hope that we might have an instrumental variable. So that goes to one of the earlier questions today. I think it was Raul who asked that. But sometimes we don't have good IVs and we're in a kind of a difficult situation, right? And more often than not, we're not allowed to make such experiments. Sometimes we have a natural experiment. That's a good thing to work with, but more often than not, we're in a situation in which we cannot really make experiments. So having this random assignment is something hard to have. So having that said, how do random forests work in this whole scenario? So maybe one first point on that. So it does not really solve our problem of not having a random assignment of the treatment. So having that said, if we have data that is observational, right, and if we do not have randomness in the assignment of the treatment, either because it was an experiment or perhaps because some units are outside of the influence of the law or of the policy decision, and we could use this perhaps as a control, or we're using the time perhaps to say, okay, this was a natural experiment, so we can compare before and after. If we don't have such a setting, it's important to note that we're still working in this world of relationships that might not be causal, right? So we're working in the world of, we're trying to do a selection on the observables, right? So important to say causal forces are not our silver bullet in this situation. But having that said, what can they actually help us with? In my opinion, the real power of causal force is that they can help us to estimate heterogeneous effects. So let's say in the typical world, let's say we have a certain treatment, this was randomly assigned, and I'm going to say, well, let me see what is the effect of the certain policy decision on banks. And I'm going to have a dummy variable, treatment yes or no. And maybe I have reason to believe this treatment might be heterogeneous depending on the size of the bank. Okay, so I'm going to interact that with some variable that I have to control for bank size. But I'm typically in a regression setting, I'm not creating 20 different interaction terms or 30, right? So typically there's a certain limit to how many interactions can I include there, because I'm going to have estimates that are not so precise anymore. So that my number of variables increases very fast if I start interacting everything with everything, including the treatment, if the treatment dummy there. So in a sense, I'm a little bit constrained in trying to understand how does this treatment vary for specific subgroups of the population, whatever my population is. And that's, in my opinion, the big boost, the big gain of a causal force, because they're being optimized, and we're going to talk about this in a second. They are optimized not only on, let me try to see what is the what is the error that I get for my predictions for my y and my y hat, but they also in the mathematical function that is used for the split. And this is something that is quite involved, but for easy of understanding, we have two factors that play a role there. One is, do I have good predictions of my y? And also the other one is, do I have estimated treated effects that are as heterogeneous as possible? Meaning, when I'm growing the tree, do I end in leaves that have the maximum possible difference in the treatment effect? And that's actually the key to understanding what is the advantage of those trees. Okay, it's not that they will let us work with observational data and say that this is causal. We still have to take this with a grain of salt, but there are quite a lot of papers arguing and also arguing mathematically that if you have enough variables there, then because these trees are making many splits to try to find very homogeneous groups, and we are controlling for many of the heterogeneities that could happen, then one could argue that asymptotically, this effect that we're measuring there can converge to the true effect. But again, that depends on what you have in your hands in terms of data.
So
okay?
In a nutshell, basically this causal forest, what we're trying to do is to get small groups of our samples which are as similar as possible, but which still contain both samples with the treatment and without the treatment. So we can, within those very similar samples, get the treatment effect estimated on the difference between those two. So in essence, we're trying to we're trying to find samples with the tree that are as similar as possible, very close together in a sense. You're still.
I see. I'm muted. Yeah. Thank you. So also important, a very good point, Sebastian. So if I would say, well, I have a candidate variable here to split with a certain value, And if I split this, oh, sorry, wanted to have my pen. And if I split on this variable, I would land here on 2 nodes. And in this node here, I have nobody that is default yes. So let's say, okay, now default is it's a bad example. So okay, it could. So let's say I have a treatment. Maybe my treatment is imagine the bank randomly asks some customers to come in person and show their documentation. Let's say this is my treatment. Okay, and I do this randomly, and imagine here that in this leaf I have nobody that we asked for to come in the bank and show the documentation in person. So in that case here, everybody is treatment 0, so I cannot measure any treatment effect here. So this is a split that the tree would not pursue because it wouldn't be able to estimate the treatment effect here. So this is also one thing that the tree considers into this growing process. So I'm trying to find splits that give me a small classification error. So I do not want to send people here and there. And actually, this would lead to predictions of the Y. So in our case, default yes or no would lead to predictions that are totally incorrect. But most importantly, in this case, the biggest weight here that determines the split is considering that I have enough treatments. I'm going to call this W. I have enough observations in both nodes that are 1 and 0, meaning I have enough people that we randomly called to come in a bank and show the documentation, enough people that we not call. Then we can go and say, let's measure here the treatment effect in both of these leaves. Yeah. And the optimization here cares a lot about how high is going to be this difference between both entities. So how high is going to be the treatment effect? And if I have a split on a certain variable and a value that gives me a high jump between both of these groups that I end up with in each of the nodes, then this is going to be the variable and the value that the tree is going to use for the split. Okay, so it's abstracting from that idea that we had before of just, I want to predict the Y very well. Instead, I want to predict the Y very well, but I also want to get the highest possible jump in the effect. Meaning, what are the splits that lead us to having leaves with the highest possible treatment effect there? Now, there is a trick here, right? Because you might say, well, okay, so if we're doing this, like in theory, imagine I have a tree that grows very, very, very much. So we're talking about the forest, but let's think of each tree separately. So for each tree, I'm learning basically noise, because maybe I end up with a group here where I have a huge effect. So this measured effect is huge, but this is something that does not generalize to most of the data out there. This was just a particular aspect of the data that I had in my hands. So here we're at, in principle, we at the very high risk of overfitting. So we find, for example, 5 observations here that are treated yes and 5 observations that are treated no. That give us a big jump in this effect, but in fact, this is something that is not generalizable. So how do we avoid that? These trees, they are grown with 2 separate samples. So we have the original data, and what we're going to do here is we're going to take half of this data. So let me finish drawing my data set. So we're going to take half of this data, or at least not always half. It can be half, but typically you're going to do half, but you could also set this a little bit differently. But typically you say you're going to take half of it and you say, I'm going to use this part of the data to decide on the splits, to say, okay, what is the variable and the value that I want to use in each split to grow my tree. So I'm growing my tree with this sample there. So this is using for growing and deciding which are the splits that are going to give me the best possible difference in the treatment effects, because we want to have very heterogeneous treatment effects there. And then the other one, that's what I'm going to use to really estimate the effect. So I'm not going to trust a priori on the effect that I got from this first part here. So this one is just using to growing, but to really see, okay, is this a shape that I got from the tree? Is this something that is actually leading to really heterogeneous effects there, and how high are these effects that we're measuring. This we do with the second part of the data set. All right, so that we can bring this to a point where we do not overfit too much to the data. Okay, and this is also behind the concept of honesty in trees. So if you're reading about called trees, this is a word that you're gonna find quite a lot. And there's even some packages that discuss it. They're building honest trees. So the idea is that at the limit, if you have enough observations, especially if this share of observations between treated yes or no in the nodes is large enough, then this should converge to a true treatment effect. Now, you might want to ask yourself, okay, but what is the advantage of using this, right? Because in principle, I said, okay, that does not really free you from having some exogenous variation in your data, or at least if you don't have any exogenous variation, you still need to make your case to any people that you're explaining the results of your analysis to, or to reviewers if you're submitting to a journal. You still need to make your case about why the selection of observables is good enough in your case. But what is the advantage here? The advantage is if you would do this in the context of a regression. So let's say I have 10 variables, so 10 independent variables, let's say 10 xi's, and I have here a treatment variable w. If I would include all the possible different interaction terms that I could get from the w's in the x's, including w times x1 times x2, w times x1, x2, x3, x, and so on, this would lead to several thousand. I think it's even more, like with the combination, it would lead to more than 2,000 different coefficients. So as we know from the regression world, that would be a killer for our regression, right? So our regression could not handle this, or even if we have enough observations to do this, our estimates would probably be very weak. So we would run into many problems there. Now with the causal forest, or with the causal trees, this is something that we can do, because again, remember, we're confronting the number of observations that we have, with one variable at a time, or one combination of variables at a time. And that lets us handle this be much larger than n problem, right? So this is not an issue here in this situation. And then that can lead us to finding very different subgroups for which the effects might be different from one another, right? So that's actually the big advantage here, in my opinion, of using that. And you might see here visually, so that's an example comparing the true effect, which in this case we know because this is just simulated data, so we don't have this lecture in reality, but here we have simulated data, so this is the true effect. And this is comparing the effect measured by causal force and the effect measured by using K and N. And we see, well, with the if we don't have a very high dimension here, so if you only have dimension of 6, then we see that, well, we can actually also do a good job with other methods. But as we're moving towards higher dimensions, then things look quite nice with causal forest, but with other methods, not so much, because they really start to suffer from the curse of dimensionality there, if you would really start making all these interaction terms with the treatment effect, right? So that's, in my opinion, the big gain that we have from using it. And if you're estimating lots of trees here, so then there you would typically not want to stick with 100 or 200. So you'd really want to have more trees so that you can also compute the confidence intervals there with a bit more precision, right? So typically you would go with a couple of thousands of trees so that you can estimate good confidence intervals there.
And since this is simulated data, we can know exactly what is going on. And this was set up in such a way that only we are seeing here 2 of the features, 2 of the dimensions. And these are set up to be the only ones that matter. The data was fed with even more dimensions in the top row, with 4 additional useless dimensions. And in the bottom row, it was fed with 18 further useless dimensions. Like I mentioned before, the idea is to find samples that are as similar or as close to each other as we can, and then determine the effect between those very similar samples, either with the treatment or without the treatment. And both k-nearest neighbors is a way to find samples that are very close or very similar, and causal forests is a way to get samples that are very close or very similar. However, k-nearest neighbors cannot help but use all of these other useless dimensions in their distance metric. That's why the more useless dimensions there are, the worse the matching of similar samples gets. And that's why in this specifically designed sample, causal forests is much better at finding close matches between treated and untreated in such a way that their treatment effect is similar and reliable.
That's a very good point. So for most methods that are out there, you don't even have an option to say, I'm going to search through this giant hyperparameter space and I'm only going to use some of them. But for KNN or for regression, they're going to use everything that you give them. And they're probably going to get very, very confused by having so many dimensions, especially all the possible combinations of them. If you're also considering all the interaction terms that we can generate out of them, they get very confused. And that's actually what we see here from this picture.
We also have a question in the chat. In causal forests, does the treatment have to be binary, either 1 or 0, or can we have a continuous variable that is the treatment? For example, the impact of hours of study on test outcomes. And well, this plot right here shows us 2 variables that have a causal impact on, in this case, the color of the outcome. So yes, we can have continuous variables. Basically, you can think of it in this way. For the binary case, we have all of our samples on one end and all of the treated samples on the other end, and we're kind of trying to get the average slope between them. So as we move from effect 0 to effect 1, what is the effect on, from treatment 0 to treatment 1, what is the effect on the outcome that we care about? And you can do kind of the same thing even for continuous variables with anything in between. Basically, you're trying to regress, so in a sense, the treatment effect depending on your treatment.
Yes, they're very good points. So you're basically looking for a slope there instead of just a difference in averages, right? So that would be something totally applicable. And there are many extensions out there. For example, in the case of multiple treatments, right? So sometimes your treatment is split into phases. So there are also extensions for that. What I'm not sure is maybe there might be also out there, because I mean there's so many extensions there. But what I'm not sure right away is whether you also already have extensions for treatments in different periods of time. So for example, I have a certain set of covariates and I measure something for this group of people. The others are treated in another period of time. Actually should be the same treatment, but maybe the environmental conditions are different. So in the econometrics, there are all these kinds of problems out there. I'm not sure whether there is already an extension for random forest to account for that, but probably there is. So if there isn't yet, there's someone working on it, I'm pretty sure. So just follow the working papers of people who are working on it. So I'd say the usual suspects are Stefan Waage, Susan Athey, there's Akin Zeilis, there's also Thorsten Hawthorne. So these are the usual crew who have been working on this topic for the past years. So follow them, and if there's no solution yet, they're probably working on it.
I mean, I'm sure you've often heard correlation is not causation thousands of times. If we want to gain any information about causality, we need to be really, really careful. We have all of these different assumptions that causal forests are all of this additional complication with the splitting set and the estimation set. All of that is just designed to make sure that we're still following these assumptions. And if we're introducing additional complications such as time series data and so on, that's making it more difficult. And I'm sure there's research being done on how to extend these models for more complicated situations. But getting causality is still difficult enough as it is.
Yes. So your argument here, if you have observational data, would still be you're doing somewhat fancier approach in a sense that you're really trying to get very, very homogeneous groups by controlling for, not only controlling for the X variables that you have there as an additional control, but you're also interacting the treatment with all of those variables there. So in a sense, let's say if we have a tree here that has these 3 splits, then landing in this node here is equivalent to having the treatments. Let's say this is a split on x1 in whatever value. This is a split on x2, and this is a split on x3. Then this is equivalent to interacting doubly with x1, x2, and x3, which is typically something that we would not do for all the control variables that we have in the context of a regression, right? Because most of the times this is something that would really cause many, many issues, multicollinearity among many, many others out there, right? So this is something that you're actually landing with when you go through those. Actually, okay, one piece of comment. It's not exactly equivalent to multiplying by x1, x2, and x3. Instead, it's equivalent by multiplying it by an indicator variable that says, for example, if the split here was x1, let's say smaller than 1, then it's equivalent to multiplying it by that. That's more appropriate, because we're not multiplying it by the, if x1 is a continuous variable, we're not multiplying by the variable itself, but instead we're multiplying it by what is the question that I asked here in the tree. And that is for a continuous variable, typically, is this variable larger or equal than a certain number? So it's actually equivalent to doing this for x1, for x2, and x3. So that leads us to having more homogeneous groups. And we have a question here, I thought. No, sorry, no
yes,
question.
We have another
we do.
question.
Oh yeah, here in the Q&A, yeah.
In the Q&A, can we quantify the direct and indirect effect that a variable x may have on y? So let's imagine there's also a third variable z, which is affected by our original variable x, but at the same time, z also affects y. So we get sort of in this triangle interaction, the direct causal effect and also the indirect causal effect. Can we separate the direct effect of x on y and the indirect effect of x on y through the third variable z? And kind of that's what the causal tree is trying to do by doing these different splits. This variable x, that's one of those variables that is used to generate the splits. And at the when we're doing the leaves of the tree, then this will sort of be represented in there. How can I draw maybe a picture?
Maybe let me stop my sharing. I'm still thinking about that. Maybe if you want to share a screen, Sebastian, maybe you.
I don't have the great.
Sorry?
I don't have such a great software as you do for drawing pictures. Maybe this will do. Like we mentioned, so we've got the variable x and we've got the variable y that we're caring about, and then there's maybe a third variable z that we care about. And when we are doing the splits, so we might have then in our data set these 3 variables that we have, and let's say we've got a well, that's actually this is fine. So let's say we've got a small y and a small x and small z. and if the x is bigger, then the z will be bigger. And so then the effect from both of these will be that this is much bigger. If the z value is independent or has its own influence, for example, this is really, really big and this is small and this is really small, basically, these will end up in different branches of our tree. Hopefully. And in this way, unless I'm mistaken, it should be able to pick this up. And then when we are applying a new sample, which we're feeding through the tree, it will, when it's finally estimating the end result, it will take into account, basically, assuming we have enough data that we trained it with, both this direct and this indirect effect for the given sample that we're looking at. And the question is, can we separate the direct effect of X and Y and the indirect of X and Y? And well, no, that's not something that the causal tree is doing. When we're feeding a new sample through here, it's basically giving us the conditional treatment effect on the data that we have. And so this extra variable Z, if that's also dependent on X, then it's giving us the overall effect, not split into direct and indirect.
Yeah, I see also we're I don't know if everybody see if you have just maybe 1 or 2 minutes, because I see we're eating time of the break, so so perhaps we continue the discussion after the break. But just one small remark: I don't think you're able to separate the effect. The effect will play a role into the decision of the splits, but I do not think that you're able to separate the effects there. But what we can definitely do is to try to figure out how much that affects our splits. We could run a simulation, so we could simulate some data, and that's going to, we should just have to figure something else to set up something. I'll try to do that until tomorrow so that we can take a look at what happens in there. Because it's not such a straightforward question, but intuitively I would say you cannot separate both. But I think this effect, this indirect effect of the treatment variable, would still play a role in the splits.
Great. So should we take our break? Yeah. Okay. Yeah. So let's be back at 10:45. Is that fine? Okay then.
All right. So see you in a bit.
Yeah.
See you in a bit.